Numeric Probability, Chapter 3. So far, the examples of probability have been in terms of particular context, like a probability of getting a flu or cancer, or probability of heads or tails, probability of a particular card. There's also some generic probability problems that you may encounter in WebAssign that do not have a particular context. They're just they're expressed in terms of probability of event A, probability of event B, and so forth. So I'll get into those a little bit, but first I want to sort of review some of the other the examples that we've done so far. And one example was the during a flu epidemic in a two-child family. Probability of the first child getting the flu is 0.4. Probability of the second child getting the flu is 0.4. Probability they both get it is 0.25. And then we use this information to compute the conditional probability, probability of the second child getting the flu if the first child gets the flu. It's the probability of both, which is 0.25, divided by the probability of the first child getting the flu, 0.4, that comes out to be 0.625. So as one might expect, since flu is contagious, the conditional probability is of 0.6 is different from the original probability of 0.4. So we say that each child getting the flu is dependent and not independent of the other child getting the flu. Okay. Another example was tossing a coin. If the coin is evenly weighted, it should turn up heads half the time and tails half the time. And the tosses are independent, so regardless of whether the first toss is a head or a tail, you still have a 50% chance of getting a head on the second toss. Or even if the first 99 tosses are heads, you still have a 0.5 chance of getting a head on the 100th toss. So when events are independent, the probability of both is the product of the probabilities. So the probability of a head and then a tail would be 0.5 times 0.5, which is 0.25. And on a single toss, heads and tails are mutually exclusive. So if you just toss the coin once, you're going to get a head or a tail, but not both. So the probability of a head and a tail on a single toss is 0. So that's a property of mutually exclusive events. The probability of both happening is 0. Also, for mutually exclusive events, the conditional probability is also 0. So the probability of a head on the first toss, if you get a tail on the first toss, is the probability of both, which is 0, divided by the probability of a tail. So it's 0 divided by 0.5, which is 0. But if we toss coin more than once, then it is possible to get a head on one toss and a tail on the second toss. So those are not mutually exclusive. If the event is a head on the first toss and a tail on the second toss, those are not mutually exclusive. Another example to review, we have a standard deck of 52 playing cards. We have 2 black suits, spades and clubs, 2 red suits, hearts and diamonds. Each suit has 13 ranks. Those are pictured on the next page. A single card is randomly chosen. Let D represent the event the card is a diamond. H represent the event the card is a heart. Q represent the event the card is a queen. Are D and H mutually exclusive? And yes, a card can't be both a diamond and a heart. So here's the picture. These are hearts and these are diamonds. So these you can't have them both. Are D and H independent? No. Probability of a diamond is 13 over 52, which is 1/4, but the conditional probability of a diamond given a heart is 0. So the conditional probability is not the same as the original probability. Okay. Are D and Q mutually exclusive? Okay, and the answer is no, they're not mutually exclusive. There's one card that is both a diamond and a queen. So the queen of diamonds here. This card is a diamond, both a diamond and a queen. So D and Q are not mutually exclusive. Are D and Q independent? And the answer is yes. The probability of a diamond is 13 out of 52, because in the standard deck of playing cards we have 13 diamonds out of 52. So that reduces to 1/4. And the probability of a diamond, if we have a queen, is also 1/4, because we have 4 queens, one of each suit. So if we know that it's a queen, then there's a 1 chance out of 4 it's going to be the queen of diamonds. So the conditional probability is the same as the original probability, so that means that D and Q are independent. Okay, continue with this example. Suppose now we draw 2 cards instead of 1 card. So the first card is placed back into the deck. The deck is shuffled, and the second card is randomly drawn. This is called sampling with replacement. We let R1 represent the event the first card is red. R2 represent the event the second card is red. And the question is, are R1 and R2 mutually exclusive? The answer is no. It's possible that both cards are red, because are R1 and R2 independent? And the answer is yes, because the conditional probabilities are the same as the original probability. So the probability of red on the first draw, 26 out of 52, which reduces to 1/2, and the probability of a red on the second draw, if the first draw is red, is still 26 out of 52, because we put the red card back in the deck, so we still have the original 26 red cards and the 52 total cards. So that reduces to 1/2. So the probability, conditional probability, is the same as the original probability. So that means they're independent. Okay, now suppose that the first card is not placed back into the deck, and the second card is randomly drawing from the remaining 51 cards. This is called sampling without replacement. Let R1 represent the event the first card is red. R2 represent the event the second card is red. Are R1 and R2 mutually exclusive? Again, they're not mutually exclusive. It's possible that both cards are red. Are R1 and R2 independent? Well, not quite. They're just somewhat dependent. They're not. They're close to being independent, but not quite. The probability of red on the first draw, 26 out of 52, which is 1/2, is 0.5. Probability of red on the second draw, if the first card is red, if the first card is red, we'll have 25 red cards left out of 51. 25 divided by 51 is 0.49. So the conditional probability is approximately 0.49. The conditional probability is not the same as the original probability. So we have 0.49 compared to 0.5. So the events are not fully independent. Okay, so let's get into some generic events now, because the examples we've done in the videos have mostly been in particular context, but some of the problems you'll encounter in WebAssign do not have any particular context. So A and B are 2 events, and let's suppose in this example A and B are independent, and we're given the probability of B if A is equal to 0.7. So we're given the conditional probability. Probability A, we don't know, not enough information is given. Probability of B, that's because they're independent, the conditional probability is the same as the original probability, so that's going to be 0.7. Probability of both A and B, that's not enough information is given. Probability A if B, again, not enough information is given. Are A and B mutually exclusive? No, because the probability of B if A is not equal to 0. So we were able to answer 2 of these questions. Some of them we didn't have enough information. Okay, so again, A and B are generic events, And this time A and B are mutually exclusive. And probability of A is 0.7, probability of B is 0.2. We want the probability of both. So if they're mutually exclusive, the probability of both is going to be 0. That mutually exclusive means that both events cannot happen at the same time. So the probability of both is 0. Probability of A or B, this is A union B, it's probability of A plus the probability of B minus the probability of both. Okay, so this will be so the probability of A is 0.7, probability of B is 0.2, and because A and B are mutually exclusive, the probability of both is 0. So it's 0.7 plus 0.2 minus 0, 0.9. A probability of B if A, so that's going to be the probability of A and B divided by the probability of A. So the probability of A and B is 0. Probability of A is 0.7. 0 divided by 0.7 is 0. So the conditional probability is 0. Probability of A given B, it's the probability of both. Probability of A and B divided by the probability of B this time. So it's going to be 0 divided by 0.2, and that's 0. Are A and B independent? And the answer is no, because the conditional probability is 0. The original probabilities were not 0, so they're not independent. The conditional probability is not the same as the original probability. Okay, example 6. A and B are generic events. Probability of A is 0.8, probability of B is 0.2, probability of both is 0.1. Probability of A union B, that's A or B or both. So it's the probability of A plus the probability of B minus the probability of both A and B. So this is going to be 0.8 plus 0.2 minus 0.1. So we subtract the overlap. So this is 0.9. If you could maybe make this clearer with a Venn diagram. So if you don't want to double count the overlap. So if this is A and this is B, where they overlap is A and B. So when you're computing the probability of both, you don't want to double count where they overlap. So the 0.8 includes things that are in A and B. The 0.2 includes things that are in A and B, events that are in A and B. So you don't want to double count the overlap. So that's why you subtract off the probability of both. The conditional probability of B given A, so that's the probability of A and B divided by the probability of A. So that's going to be 0.1 divided by 0.8, and that's 0.125. Okay, probability of A given B, that's the probability of both again, divided by probability of B, 0.1 divided by 0.2, 0.5. Are A and B independent? So no, because the conditional probabilities are not the same as the original probabilities. So the probability of A is 0.8, the probability A given B is 0.5, so those are not the same. So they're no. Are A and B mutually exclusive? And the answer is no, because the probability of both is 0.1, which is not equal to 0. Okay, so this is another review of something we did before. A test has been developed to detect a certain type of cancer. The test correctly identifies 95% of cancerous people as cancerous and correctly identifies 80% of non-cancerous people as non-cancerous. It's known that 0.2% of the population has this type of cancer. In this example, we were given a conditional probability, the probability of test cancer if the patient actually has cancer. In a clinical setting, we would like to reverse the condition and compute the posterior probability of cancer if the test says cancer. And we use a tree for this computation. You could also use Bayes' formula. Okay, so here's a sort of a generic example. So I like to include some examples that give you an idea of how this is actually used, but in the text and in the WebAssign you'll also see some sort of generic examples that do not have any particular context. So we're given probability of A is 0.1, conditional probabilities, probability of B if A is 0.8, probability of B complement if A complement is 0.6, and we want to find some additional probabilities. And a tree is going to be helpful for this. You could also use Bayes' formula, but I like to use a tree. I think the tree kind of helps your intuition more than Bayes' formula. So we're given probability of A is 0.1, and that means the probability of A complement is 0.9. It's 1 minus 0.1 is 0.9. So, and then we're given conditional probabilities. Either B is true or B complement is true. So we're given the probability of B if A, that's 0.8, and that means the probability of B complement if A is going to be 0.2. That's 1 minus 0.8 is 0.2. We're also given the probability of B complement if A complement is 0.6, and then if you subtract 1 we get 0.4. And then to get the intersections, we want to multiply. 0.1 times 0.8 is 0.08. That's the probability of A and B. 0.1 times 0.2 is 0.02. That's the probability of A and B complement. 0.9 times 0.4 is 0.36. That's the probability of A complement and B. And 0.9 times 0.6 is 0.54. That's the probability of A complement and B complement. Okay, so then we can go back and answer our questions. Probability of A and B, that's 0.08. That's from the tree. Probability A if B. So the probability of, that's going to be the probability of both, divided by the probability of B. So the probability of both is that's the 0.08. And then there's two paths where the event B occurs. That's the 0.08 and the 0.36. But they both have a B without the complement. So it's 0.08 plus 0.36. 0.08 divided by 0.44. And that's going to be 0.18 and repeating 1/8. It's a repeating pattern. Okay. And then probability of A complement if B complement. So that's going to be probability of both A complement and B complement, divided by probability of B complement. Okay, so the probability of both, that's the 0.54. And then there's two paths where the event B complement happens, the 0.54 and the 0.02. So on the bottom we're going to add those two. So it'll be 0.54 divided by 0.56. I get 0.96 something. 964285714. Okay, so let's say approximately 0.964, and this is approximately 0.181. Okay, so are A and B independent? So they're independent if the conditional probability is the same as the original probability. So we're given the computed probability A given B is 0.181 something. The original probability of A, if we don't know B, is 0.1. So they're not independent. Are A and B mutually exclusive? For mutually exclusive events, the probability of both should be 0, but the probability of both here is 0.08, which is not 0. So these are not mutually exclusive. And that concludes this presentation.